This is the lecture and slideshow for weeks 12 and 13. These slides will cover 2 weeks of the course, the 12th and the 13th week. There will be only one more set of slides after this. That set of slides will cover weeks 14 and 15. For this set of slides, read handout 6 in Okasha chapter 3. Also explore the material I have for you in Canvas module 6, especially these. Let's review. I talked last time about underdetermination. Underdetermination happens when incompatible rival hypotheses are consistent with the same evidence. Recall that we want to explain what we observe. From Earth, we observe that Venus has phases, variations in lighting on its surface, just like the waxing and waning of our orbiting moon. And we also notice from Earth the sunrise and the sunset. That is, the sun appears to revolve around Earth. The sun orbits Earth, but the other planets orbit the sun. This was the explanation Tycho Brahe favored. The same evidence, however, is consistent with another hypothesis. The hypothesis itself is not compatible with Tycho Brahe's hypothesis. That hypothesis is that of Galileo Galilei, following Nicholas Copernicus. He thought that would explain these observations, this data, was that Earth orbits the sun and so do the other planets. And the point behind underdetermination is that we can't rationally choose or favor one hypothesis over another unless further evidence emerges. This isn't true for all rival hypotheses. We can recast these explanations, the hypotheses, as standard form rationales, enabling us to evaluate each. And I'll do this later in the lecture. Have a look at this now. From the previous slide, we should see that hypotheses 1 and 2 are different, rival, causal hypotheses. See handout 6 for more on this. Stated simply, Earth appears to revolve around the sun and Venus has phases like our moon because hypothesis 1. Or, Earth appears to revolve around the sun and Venus has phases like our moon because hypothesis 2. First, you state each causal hypothesis as a different explaining reason for the same phenomenon. That is, whatever observations, evidence we want to explain. Second, in the conclusion of the rationale, let's state the phenomenon to be explained. Science is a repository of explanatory arguments and theoretical models passing pragmatic criteria of acceptance. That is, a theory unifies our beliefs when it provides a pattern of argument which can be used to derive many other claims we tentatively accept already. But this does not make it true. For example, Darwin's theory of evolution by natural selection unifies many biological phenomena, patterns of organic similarity and diversity, and the curious fit of organisms to their environment now make sense. We now have an uncertain but testable theory, tentative and useful for describing, predicting, and explaining, when before Darwin we had an untestable, dogmatic, and scientifically unhelpful article of religious faith explanation, namely God did it, the God hypothesis, which was only ever at best a plausible description. Here is a way to look at how science proceeds. Call this its standard operating procedure. First, you describe precisely the phenomenon observed. Next, produce an argument for accepting that such phenomena occur. Third, you assess the evidence. Fourth, you produce multiple explanations of the phenomena. Test rival explanations. Produce an argument for accepting the best available explanation. 7, accept tentatively that explanation which explains best. So what exactly are explanations? Here's a phenomenon we notice: the sun is hot. Why should I believe the sun is hot? Is a different question than what causes the sun to be hot. The former question seeks an argument. The latter question seeks an explanation. Here are several things you need to know about arguments versus explanation. We begin with this. Arguments answer the question, how do you know? Unlike explanations, which answer the question, why is this so? Here's a diagram comparing and contrasting two kinds of rationales, arguments versus explanations. Arguments and explanations both have conclusions. However, their reasons function differently. An argument is a rationale designed to convince us of the truth of a conclusion by giving reasons, which are evidence for accepting that conclusion. An explanation is a rationale designed to help us understand a fact or event by giving reasons specifying its causes. We seek knowledge and understanding. Each results from two separate kinds of reasoning, arguing and explanation. If we want to justify believing that P, something occurs, the sun is hot, then we produce a valid or a strong argument. We do this by presenting relevant evidence for P. Now, if we want to say why P is the case, why the sun is hot, then we produce an explanation. We do this by describing causes of P. You can know something without understanding it, right? For example, you can know that the sun is hot without understanding why the sun is hot, what makes it hot. You can know that you don't like someone without knowing why you don't like someone. Now, arguments give us knowledge, but only explanations can give us understanding. An argument answers a different question than an explanation, even though both rationales have the same conclusion. The sun is hot, because scientific observations reveal that it is approximately 6,000 degrees Celsius on its surface and 16 million degrees Celsius in the center, versus the sun is hot because thermonuclear fusion of hydrogen atoms occurs within it, and this produces a huge amount of energy in the form of heat and light. So here's the argument. The sun is hot because observations reveal that it is approximately 6,000 degrees Celsius on its surface and 16 million degrees Celsius in the winter. Notice that this argument does not explain why the sun is hot. For that, we need a rationale about what causes the sun to be hot. Here's the explanation. Why is the sun hot? The sun is a huge nuclear reactor, and some of the energy it produces travels through space as very intense light waves. Since our sun is 93 million miles away, only a small fraction of its total power reaches Earth. Notice what explains the hotness of the sun does not justify our believing that it is hot. For that, we need an argument. Summarizing, knowing something is not the same thing as understanding something. Knowing a fact, knowing that the sun is hot, is not the same thing as understanding why the sun is hot. And so that's the difference between arguments and explanations. Arguments give us knowledge, can give us knowledge, and explanations give us understanding. Explaining reasons are not the same thing as justifying reasons. Let's practice understanding the difference between arguing and explaining. They're not the same thing, though people in ordinary language use the terms interchangeably. That's a mistake. See my rationale samples handout. For each of these claims, I want you to write down two rationales for each conclusion. That is, produce an argument for each of these, and produce one explanation. I'll go ahead and look at this one, number 6. Butch is afraid of clowns. Butch is afraid of clowns. I want an argument for that and an explanation for that. I want a justification for believing that, and then I want to know why. Here are two rationales. Each has the same conclusion in boldface below. That is, for each conclusion, one may construct an argument and an explanation. Butch is afraid of clowns because whenever he sees a clown, he becomes nauseous, has trouble breathing, his heart rate escalates, he trembles and sweats profusely. So this argument justifies believing he's afraid of clowns. It answers the question, why should we believe the conclusion? All right, here's an explanation. Butch is afraid of clowns because he was kidnapped and tortured by a clown when he was a child. This explanation answers the question, why is this conclusion true? So what again is the difference between an argument and an explanation? Arguments justify accepting conclusions, but explanations tell us why conclusions are true. Explanations do this by specifying causes. Reasons that justify belief in an alleged fact, Butch is afraid of clowns, are not the same as reasons that explain that fact. Let's review what a scientific theory does. What is the point of science? Science aims to describe reality. explain phenomena and justify beliefs in descriptions and explanations. What's the difference between an argument and an explanation for some batfish have red lips? Arguments give reasons that justify belief. Explanations give reasons that specify causes. Some batfish have red lips because photos from deep-sea dives reveal this trait. People dive in the ocean and see that fish, look at those red lips. That establishes the fact that they have those red lips. Now, this argument can be deductively valid or inductively strong, even if its assumptions are false. Doesn't matter. The idea is that an argument is supposed to provide proof, justification for belief. Some batfish have red lips because red lips repel predators but attract prey and mates. That's an explanation. Is it true? It doesn't matter at this point. An explanation can be plausible, can account for data, even if its assumption or even if its conclusion is false. It might not be the case that batfish or any batfish have red lips. The idea here, though, is that what could explain it, is that those lips have a function. Third point. For any rationale, identify the conclusion and reconstruct its form so as to expose its reasoning. Here's a strange phenomenon from early colonial American history. In January of 1692, 8 young girls became ill in Salem, Massachusetts. They suffered from delirium, violent convulsions, incomprehensible speech, trance-like states, visions of strange animals. Villagers concluded that these girls were under a spell, bewitched by members of their own pious community. Here are 2 rationales. Several girls in 1692 Salem suffered delirium, strange visions, and violent convulsions because transcripts of court proceedings and testimony document this. That's an argument. Several girls in 1692 Salem suffered delirium, strange visions, and violent convulsions because they were possessed by demons. That's an explanation. We don't want to confuse whether something is an explanation with whether it's a good one. Same goes for explanation. You could have a rationale which explains an alleged fact, even if what's believed to be a fact is not the case. One more. Here I'm unpacking the parts of each rationale to expose the principles which connect statements about observations with conclusions that either justify belief or explain. We want to justify believing Earth spins 1,000 miles per hour around its axis, approximately. We also want to explain it. Well, Earth spins around its axis 24,000 miles in 24 hours. It completes 1 revolution in 24 hours. If X spins 24,000 miles in 24 hours, then X spins 1,000 miles per hour. Mathematical principle. Therefore, Earth spins 1,000 miles per hour around its axis. That's a reason to believe. Earth has been spinning since the formation of our solar system. Every object's rotational momentum stays constant unless an external force acts on it. Therefore, Earth spins 1,000 miles per hour around its axis. Notice, in each of these, claim 3 and claim 6, which are identical, we say Earth spins 1,000 miles per hour around its axis. This is the phenomenon we want to establish, provide evidence for believing occurs or is real, and it's also what we want to explain. It takes a while and lots of examples to see the difference. Look closely at how each rationale has a different function. One justifies believing while the other explains why. Here's the 4th thing you need to know about arguments versus explanations. Always disentangle arguments from explanations before evaluating them. They sometimes co-occur. We get confused. Here's a line from a movie I enjoyed. I see you're drinking 1%. Is it because you think you're fat? Because you're not. You could be drinking whole if you wanted to. So this is complex. We've got to unpack this. Here are 2 rationales. Each has the same conclusion. Deb, Napoleon's friend, drinks 1% milk, is what we want to give reasons for believing It's what we want to explain. Napoleon sees his friend Deb drinking milk from a container labeled 1% milk. And in general, if X sees Y drinking a container of milk labeled 1%, then Y is probably drinking 1% milk. And so we may conclude Deb drinks 1% milk. What justifies believing it is that the container says so, and we presume the container has not been altered. Let's look at the explanation. Deb wants to manage her weight. She thinks she is fat and does not want to gain any more weight. If Y wants to manage Y's weight, then Y drinks 1% milk, which has fewer calories. General principle here. Therefore, Deb drinks 1% milk. So what explains her drinking the 1% milk is she's trying to manage her weight. Arguments may be valid, even if their assumptions are false. Now, an argument with false assumptions, at least one false assumption, is going to be a bad argument. Still, its form could be such that if everything it had assumed was true, then the conclusion would necessarily follow. So I made this point earlier when I talked about scientific reasoning. An argument can be valid but not good. Explanations, similarly, may be successful, compelling, even if what they explain is not really happening, isn't true. Let's look at this. You need to read by now the article by Professor Randy Mays within the Moduling Canvas. It's called Beware the Convincing Explanation. He has several examples that will help you understand this important difference. You see, explanations can be too good to be true. A convincing explanation succeeds in convincing us that its conclusion is true, without ever giving us any evidence for believing that what it explains is actually true. For example, have you heard this? Upon death, the human body loses 21 grams of weight because that's when the soul leaves the body. That's an explanation. Children receive toys on Christmas from Santa. Why? Because Santa rewards them for good behavior. And you're already imagining the other explanation. Only good people who accept Jesus as their personal Savior go to heaven when they die, because God rewards the righteous and punishes the wicked. That explains why some people go to heaven and some people do not. Watch the video, Does the Soul Weigh 21 Grams? It's short. It's in the Canvas module on the page that says watch these videos for this module. This is an image. This doesn't work when you click on it. Beware of the convincing explanation. Here is a highly convincing explanation, partly because most of us will agree that we spend a great deal of time engaging in these behaviors. Still, the causes it lists just assume without evidence that this phenomenon exists. This is Professor May's example. Our thinking skills are eroding at an alarming rate as a result of our constant immersion in superficial multitasking activities. Our habits of emailing, texting, updating our status on Facebook and Twitter, and mindless channel surfing all conspire to distract us from the careful and critical habits of mind required to grasp complicated issues and engage in meaningful social relationships. Much of this rings true. But first, we need to establish that thinking skills actually are eroding, and this doesn't do it. Second, we need to consider alternative explanations even if we assume that our thinking skills are eroding. Not just this one. Third, realize that the best available explanation might not be true, even if it does explain. In fact, there is little evidence to support, despite people believing this, that our thinking skills are actually eroding as a result of our internet activity, attempting to multitask. We've been multitasking for 100 years. The distinction between argument and explanation ultimately rests on these facts. We have different criteria of adequacy for arguments and explanations. Very good explanations of alleged facts, that is, those that raise our understanding a great deal, don't provide the evidence required to accept them as facts in the first place. For that, we need an argument. So you're seeing now, when you're going to make the case for a theory, you're going to have to produce an argument for believing that what you're trying to explain happens, and then you've got to provide an explanation, and then you've got to provide an argument for accepting that as the best explanation, given rival explanations. Unless explanations are about previously established facts, they don't support belief in a conclusion. Always seek a good argument that supports alleged facts. Remember, what can be asserted without evidence can be dismissed without evidence. The best scientific theories describe and explain actual facts supported by good arguments. Here's the last of several things I want you to know about arguments versus explanations. Only causal arguments, arguments about causes, provide good reasons for accepting explanations. See my handout 6, especially section 15, for an outline of how causal arguments proceed. A causal hypothesis is an initial speculation about a causal claim. A causal claim asserts that one event causes or produces another. So a causal hypothesis explains or describes the cause of an event, say the sunrise and sunset. A causal argument provides evidence for accepting a causal hypothesis. A causal argument provides reasons for accepting, believing, an explanation. So it's an argument about what causes something. That is, a causal argument provides reasons for accepting any explanation. Now, look again at these two causal hypotheses, H1 and H2, from our previous discussion in Canvas on underdetermination and an earlier slide in this lecture. Each hypothesis is part of a different explanation of the sunrise and sunset, the phases of Venus-Moon. Here is that original slide again. You need to see two different explanations for the same phenomenon. Go back and review it if you must. The point here is that H1 and H2 explain differently, incompatibly, the very same data. Simplifying, we may say H1 explains P. H2 explains P. Of course, other, as yet unspecified hypotheses will explain P as well. Now, how do we decide which of the available hypotheses explains P best? That is, what tests, what further observations will separate the good explanations from the bad ones? Quantum physicist David Deutsch offers some advice. Watch his video. It's a TED Talk on recognizing good explanations. There is a link on the Watch These Videos page within the module in Canvas. Deutsch says we should seek good explanations that can't be varied with untestable or dubious assumptions while still accounting for data and phenomena. And by varied, he means adding things in to make it sound more plausible, perhaps things or alleged facts that themselves have not been established. The search for hard-to-vary explanations is the origin of all progress. In science, two bad approaches blight progress. One is well-known, untestable theories. But the most important one is explanationless theories. For instance, when you're told that an event is a miracle or that prayer or a potion heals, but you aren't given a hard-to-vary account of what causes it, you're being told a wizard did it. But magic doesn't explain. Is this a good explanation? Here is the causal theory of explanation. Improbable events occur, so we need more than statistically relevant correlations. Forest fires and plane crashes happen because of highly improbable correlations of predictably devastating events. But why exactly does each one occur? To explain a singular event, like this forest fire, is to give information about the prior relevant history of that event. To explain a regularity, most forest fires like this one, is to give general information about the prior history of all instances of this regularity, all examples of forest fires. How do we best explain this? That's the question. The best explanations specify causes that make their effects more likely. Here's an example. Suppose we explain a forest fire by saying a lit match caused it. The lighting of the match by itself is not sufficient. Many matches are lit without ensuing forest fires. The lit match is, however, a part of some set of conditions that are jointly sufficient for the fire. Moreover, given that this specific set of conditions occurred rather than some other set sufficient for fire, the lighting of that match was necessary. Fires do not occur in similar circumstances when lit matches are not present. Causes, then, are factors which make their effects more likely, not necessary. But an effect may still happen in the absence of that cause. or fail to occur in its presence. John Mackey proposed that a cause is an inus condition, I-N-U-S. What is typically called a cause or a causal factor is neither necessary nor sufficient for its effect, some phenomenon, some event we want to explain, but instead it's what we'll call an insufficient, non-redundant part of an unnecessary but sufficient condition for the event. You want to describe what it took to make an event happen. But it turns out there are alternative explanations and multiple causal factors. For example, media violence causes urban youth violence, or smoking causes lung cancer. Smoking doesn't always cause lung cancer, and lung cancer is not only caused by smoking. Thus, a cause is a special sort of sufficient condition for its effect. So how exactly are causes relevant to effects? Here I want to show you Mackey's account of a cause as a factor, an inus condition. So we have some phenomenon we want to explain, say lung cancer in a smoker or a forest fire. Suppose the following propositions are true. All ABC or DGH or JKL are regularly followed by P, and all P, the phenomena, are regularly preceded by either ABC or DGH or JKL. Here, the green ABC, the blue DGH, or the red JKL, see, those are different hypotheses or theories. They're alternative explanations. We could say the green theory, the blue theory, the red theory. Their component letters represent the causal factors. That's what the causes are. ABC or DGH or JKL, that entire claim represents a condition which is both necessary and sufficient for P. Each conjunction, such as ABC, represents a condition which is itself sufficient but not necessary for P. And the point is, it's either the green theory, the blue theory, or the red theory, the ABC, the DGH, or the JKL. Choose one of those. It is necessary and sufficient to explain P, but so are the others. So ABC, the green theory, is a minimally sufficient condition. None of its conjuncts, its components, is redundant. No part of it, such as AB, is itself sufficient or enough to generate P. But each single factor, such as a lit match, A, is neither a necessary nor a sufficient condition for P. That is, A or B or C is related to P in an important way. Each is an insufficient, non-redundant part of an unnecessary but sufficient condition for P. So, a cause is really a causal factor, an inus condition. Here is the actual death certificate for a typical victim of the Spanish flu pandemic. This is my great-grandfather. Pneumonia is inflammation of the air spaces in the lungs due to an infection, and it can be lethal. It's caused by viral infections, bacterial infections, fungi, any of which is an inus condition in this way that Mackey describes causal factors. Take a moment and look at this death certificate. Look at the fields where they describe the cause of death as pneumonia and the contributory or secondary cause being influenza. The 1918 flu pandemic from January of 1918 to December of 1920 was an unusually deadly influenza pandemic. It infected 500 million people across the world, including remote Pacific islands and the Arctic, and killed 50 to 100 million of them, 3 to 5% of the world's population, making it one of the deadliest natural causes in human history. The 1918 pandemic predominantly killed previously healthy young adults. Why? What explains this? Most influenza outbreaks disproportionately kill juvenile, elderly, or already weakened patients. Modern research using virus taken from the bodies of frozen victims has concluded that the virus kills through a cytokine storm, an overreaction of the body's immune system. So this is the explanation. The strong immune reactions of young adults ravaged the body, whereas the weaker immune systems of children and middle-aged adults resulted in fewer deaths among these groups. Here is an application of the causal model. Look at the Henle-Koch postulates. Researchers, immunologists, use logically necessary and jointly sufficient conditions for establishing a causal relation between a specific microorganism, M, say Bacillus anthracis, tuberculosis bacillus, Vibrio cholera, and a specific disease, anthrax, tuberculosis, cholera. The suspect microorganism M must be present in every case of the disease. M must be isolated from the diseased host and grown in pure culture. The disease should be reproduced when a pure culture of M is inoculated into a healthy, susceptible host. M must then be recoverable once again from the experimentally infected host. Anthrax begins like an insect bite, becomes a fluid-filled blister. Its center turns black and becomes sunken. It's treatable, but it can also kill you. And this is it, Bacillus anthracis. That's the bacterium that caused anthrax. And Henle-Koch postulates were what was used to establish that the necessary and sufficient causal factor for Bacillus anthracis to cause anthrax is that it's present. Next, I summarize causal reasoning basics. See the handouts in Canvas Module 6 for more detail. We all know the difference between correlation and causation. Here's correlation. 100% of people who breathe die. There's this correlation between breathing and dying. Causation. 100% of people who don't breathe die. In this case, it's the lack of breathing, lack of oxygen that causes the death. Recall that correlation is the same thing as an association, which is another way of saying there's a link. But none of those terms refer to a causal connection. And this is the issue. We hear that a link has been established, or that a correlation has been found between two factors. And we infer, draw the conclusion, hastily, mistakenly, that the link indicates that there's an actual connection. There might be, but it might be accidental. Causal explanations require that correlations occur between causal factors, that is, alleged causes and their effect. If investigators do not observe at least an association between A and B under controlled circumstances, peer-reviewed randomized controlled trials, then you can't go on to conclude that A causes B. PRCTs are a superior way to establish correlations and then test for causal connections. Anecdotes are the worst way to show this. A causes B is ambiguous unless the context is specified clearly. When someone is not being absolutely clear, be open to interpreting any causal claim in either of three ways. To say A causes B is to say, for example, A is a sufficient condition for B, a necessary condition, or both necessary and sufficient. A sufficient condition for B is not the same thing as a necessary condition. A sufficient condition is one way to make B happen. A necessary condition is going to be an essential way, a way without which B would not happen. There might be other necessary conditions. And if you could specify all of the necessary conditions, you'd have necessary and sufficient conditions. The most charitable way to interpret A causes B is to say that A is sometimes one way to produce B. But there might be other ways. Logic offers the following possible senses of cause, but none of these is perfect since causation is poorly understood, despite the frequency with which we use the concept. A is a sufficient cause for B, as in electrocution causes death. Electrocution is one way to cause death. Hanging, poisoning, firing squad is another. A is a necessary condition for B, as in clouds cause rain. You just can't have rain without clouds. A is both necessary and sufficient for B, as in force causes a body to accelerate. No acceleration unless you've got a force, and a force is all you need to cause acceleration to occur. Use these guidelines for thinking about and testing possible relations between causal factors, conditions, as necessary or sufficient conditions for phenomena you want to explain. If A is present, but B is absent, then A is not a sufficient condition for B. If A is absent, but B is present, then A is not a necessary condition for B. Now, if you want to avoid or prevent a particular effect, E, then you should block any necessary condition for E. If we want to block viral infection, then we want to block exposure to virus particles. If you want to produce an effect, say immunity to the coronavirus, then you have to satisfy a sufficient condition for E. And a sufficient condition might be something like vaccinate them. Lots of causal stories about what causes what, may explain a phenomenon. Work toward the most likely explanation. Plausible, popular, or merely possible explanations are not more probable than any other such explanation. Be careful not to like the first clever explanation that comes along. Accept, tentatively, only that explanation that accounts best for all available evidence. When we make observations and are considering several causal hypotheses to explain what we observe, say H1 and H2, we should infer H1 rather than H2 if and only if H1 is a better explanation than H2. That is, we use what I'll call the surprise principle following Elliott-Sober. What is the surprise principle? In observation O strongly favors H1 over H2 when the following two conditions are satisfied, but not otherwise. If hypothesis 1 were true, you would expect a specific observation to be true. And if hypothesis 2 were true, you would expect that specific observation not to be true. So you're going to use the same observation to eliminate one of the theories. That is, 1, if H1 were true, then the observation would be unsurprising. And 2, if its rival, hypothesis 2, were true instead, that observation would be surprising. I'll return to this with an example in the next lecture when I discuss what makes a scientific theory good. Okay, recall the case of Bigfoot sightings in the Sierra. If a new species of forest ape lived in the Sierra, we would expect to observe that its DNA would be that of an undiscovered ape. This would be unsurprising. However, if a Bigfoot sighting was fake, then we would not expect to observe DNA of an undiscovered ape. This would be surprising. Thus, the unique DNA sample, the prediction that we would see unique DNA if we recovered it from the body, would rule out the hoax explanation, since the new species of ape hypothesis explained the predicted observation better. Finally, we should expect complexity. Often many different causes contribute to an overall effect. Never rule out accidental correlations or common cause explanations until exhaustive statistical tests of correlations have been done. The best explanation must explain better and with fewer untestable assumptions than its rivals. Correlations always have alternative explanations, so always consider and test at least 3 possible explanations before testing them against each other and then settling on one. Here are 3 explanations of Bigfoot sightings in the Sierra. Hypothesis 1, it's a man in a gorilla suit. Hypothesis 2, it is an as yet undiscovered bipedal forest ape. Hypothesis 3, it is a genetically modified organism the government released near black ops sites to scare and distract locals from discovering hidden black ops sites. Well, hypothesis 3 is more complex, but it has more things we cannot test. Up next and last will be the combined week 14 and 15 lecture. This will be the last lecture, in which we discuss naturalism versus supernaturalism, or how religious and scientific worldviews conflict. For this and the rest of the course, you need to read the entire text, Science and Religion, Are They Compatible? By Daniel Dennett and Alvin Plantinga. Our topic questions will be the following. What makes a theory scientific, and what makes a scientific theory good? In what ways are mainstream religious worldviews and modern scientific worldviews incompatible? This is the end of the second to last lecture slideshow.